Welcome to this introduction to blockchain. My name is Javier Varela. I'm a postdoctoral researcher at the Microelectronic Systems Design Research Group of the Technische Universität Kaiserslautern in Germany, and I will be guiding you throughout this video. It all became widely visible thanks to a white paper titled Bitcoin, a peer-to-peer electronic cash system, which was published in late 2008 under the pseudonym Satoshi Nakamoto. The first version of Bitcoin became available a few months later, in early 2009. Now, Bitcoin is a cryptocurrency, it's a form of electronic cash. It is decentralized, it does not need a central bank. Transactions are verified by a network of nodes through cryptographic algorithms and recorded in a public distributed ledger, which is the blockchain. It is based on a peer-to-peer network and uses a consensus mechanism known as proof of work. Now, bitcoins are created as a reward for a process known as mining. Mining complexity grows over time. In a peer-to-peer network, the nodes are connected to each other, which is different from a centralized network where the nodes will be connected to a central node, for example, a server, which is acting as a middleman. In the case of monetary transactions, this will be the bank. Now, the problem with a peer-to-peer network is that one has to assume that some of the nodes or the communication with some of the nodes might not be reliable. This is a very well-known problem called the Byzantine generals problem, where generals in an army have to coordinate an attack and reach consensus, assuming that some of the generals might not be reliable or that the messengers that they are using to send messages between each other might get corrupted. And here is where blockchain can be applied. In very simple terms, a blockchain is an electronic register with updating entries. These entries can be, for example, digital records, events, transactions. And it provides an authentic documentation history with a trustworthy update mechanism. It is based on three basic principles: continuous registry, distributed trust, there is no central authority, and cryptography, in particular, hash functions and public-private keys. The single unit in a blockchain is a block. Each block will contain several fields with information. In the case of Bitcoin, for example, we are interested in registering transactions. Each block will also have a timestamp, information about the block itself, and a nonce. A nonce is defined as a number that is used only once, and its importance will become evident in the coming slides. There is another field that will be covered soon, and finally we need to obtain the block hash. To do this, we take all the information in the block and apply a hash function, for example SHA-256. This will give as an output a 256-bit long word that can be considered as the cryptographic fingerprint of the block. Now, the length of the hash is constant, it's 32 bytes, and is independent of the amount of information that we have in the block. In order to assemble the blockchain, we need to link the different blocks, and we do so by making a copy of the hash from the previous block. In other words, if we want to add a new block, we will take all the information that we want to register, in this case the transactions. We take the timestamp, the additional information for the current block, and the corresponding nonce. We make a copy of the hash from the previous block, take all this information, apply the hash function, and obtain the hash for the current block. If you remember, the block hash can be considered as the cryptographic fingerprint for the current block, and its importance can be highlighted with the following example. If an attacker tries to modify transactions on a previously registered block in the blockchain, then the corresponding hash value will change. However, this will not match with the copy already existing in the following block, therefore damaging the logical link. As long as the attacker does not hold the majority of the computing power in the network, this attack will not succeed. The blockchain is basically a ledger that grows over time as it is updated. In a centralized network, we'll have one centralized ledger. However, in a peer-to-peer network, each node will have its own copy of the ledger, and this is called distributed ledger technology, or DLT for short. Now, the question is how to add new blocks to the distributed ledger. Mining is the process by which new blocks are created. The miner will communicate the new block to all the other nodes. The nodes will in turn check the validity of the new block. There might be a second round of discussion between the nodes, but eventually each node will agree to place the new block in their copy of the ledger. The miner will get a reward in terms of, for example, bitcoins, in the case of bitcoins, for the work done, and there is certainly an incentive for all the miners to increase their profits. There are, however, key points to consider. A peer-to-peer network will most likely look like this, where not all nodes are connected to each other. One should assume from the very beginning that the network is neither reliable nor secure. The network itself will be heterogeneous. For example, the different nodes will have different computing power and different specifications. The topology might change over time. The latency in the network is not zero. Bandwidth is finite, and the transport cost is not zero. And of course, the question is who administers the overall network? Blockchains face several challenges in practice. One of them are rogue or faulty nodes. These nodes have a negative effect on the behavior of the entire network, and the system has to be designed in such a way that the effect of these nodes over the distributed ledger does not prevail over time. Another challenge in practice is latency. Latency in a typical network is not zero, and this gets even worse in peer-to-peer networks where not all the nodes are connected to each other. Now, the problem with latency becomes more evident when several nodes propose different blocks at almost the same time. Now, because the system has to be designed in such a way that is robust against faulty nodes, this leads to a situation where the ledger is not consistent across the entire network. This generates what is called a fork at system level, and it gets even worse with more complicated topologies. There are, of course, certain mechanisms that can be implemented to either prevent or correct this situation. Now let's concentrate on mining. You might have realized from the previous slides that the hash values for different blocks are very different from each other. However, they all share a common pattern, and that is that they all start with a minimum number of zeros. Now, this is not so by accident, but rather by design. And here is where the nonce comes into play. The way mining works is by proposing a certain nonce. This can be obtained from a counter or a random number generator, and obtain the hash value for the block. And we check whether it starts with the required number of zeros. If it's not, we discard the nonce and we start all over. Now the process is repeated over and over until eventually the right nonce will be found. And this is the hash value that will be assigned to the block. This process, this mechanism, is called proof of work, and it is the one that is widely used by Bitcoin. Now, proof of work is one of the consensus mechanisms available. As we have just seen, it consists of repeating the computation of the hash value for a given block using each time a different nonce until the hash value starts with a predefined minimum number of zeros. Now, this is a very compute-intensive approach, and the miner who creates a valid block is therefore rewarded. However, this also requires a high energy consumption. In fact, the energy consumption worldwide of Bitcoin is nowadays comparable to the energy consumption of a medium-sized country in Europe. There are other alternatives, for example, proof of stake, which is becoming more popular, proof of elapsed time, practical Byzantine fault-tolerant mechanism, the Ripple protocol consensus algorithm, and many others, each with its own characteristics. So far, we have only considered the registry of transactions in the blockchain, like for example, in several cryptocurrencies like Bitcoin. However, this can be generalized into something much more powerful called smart contract. Smart contract is nothing more than a piece of code that is stored in the blockchain and that will be executed every time a certain number of conditions are met. One example of smart contracts can be found in Ethereum. Ethereum is an open source, public, blockchain-based distributed computing platform. It supports transaction-based state transitions. Ethereum provides a decentralized virtual machine which can execute scripts, which are the smart contracts, using a network of public nodes. Ether is a cryptocurrency generated by the Ethereum platform. It can be transferred between accounts and used to compensate participant mining nodes for the computations performed. Gas is an internal transaction pricing mechanism, which is used to mitigate spam and at the same time to allocate resources on the network. Let's now make use of an application example to put into practice many of the concepts that we have previously seen. In this case, we are interested in obtaining an insurance policy for a vehicle. We may assume that the vehicle will be continuously generating sensors data, and that this data will be stored in, for example, the cloud. The vehicle will do so using a digital certificate for authentication. Now, we may also assume that this data is being shared with both the car manufacturer and the insurance company. And the car manufacturer might be required to communicate on a regular basis with the insurance company as well. As we gather new data, this data will be registered in the distributed ledger. The user would obtain from the insurance company a policy in the form of a smart contract. This contract will be registered in the corresponding ledger. In the event of an accident, the insurance company has both the history and the updated information coming from the user and validated by the car manufacturer. Then, based on the policy, the insurance company would decide to transfer the corresponding funds to the user. These funds might be in the form of a cryptocurrency, and the transactions will be stored in the corresponding ledger. Now, as you can see, in this application, there is no need for a middleman. The entire application is fully automated. This example covers four main topics. The first one is the registry of data in the distributed ledger in the blockchain. The second one is the registry and execution of smart contracts. The third one is the registry of transactions and the use of cryptocurrencies. And the fourth one highlights the fact that this is a fully automated process that does not require a middleman. Let's now highlight the main advantages of using blockchain technology. The first one is data integrity. The use of cryptography, and in particular hash functions, makes it almost impossible to change data that has been previously stored in the blockchain. The second one is reliability. Since it's decentralized, it is almost impossible to fail. Data is stored in near real time, and the throughput will depend on each application. And fourth, analysis and transparency. The transactions and their impact on the various contractors is visible and transparent. There are many possible applications for blockchain technology. The most evident one is banking and finance, but it can also be used for audit and regulatory compliance, for example, since one can track backward in time all the data that has been registered in the ledger. Insurance, as we have seen in the example, counterfeit protection, real estate, intellectual property, supply chain management, health records. In this case, the records might be encrypted before they are registered in the ledger, identity management, which is a very interesting topic, as well as energy markets, and many more. To summarize this presentation, blockchain is a sum of several components. The single unit is a block, and we have seen how we use cryptography, in particular hash functions, in order to obtain the block hash. and how we use the block hash to make the logical link between the different blocks in the chain. We also make use of the so-called distributed ledger technology on a peer-to-peer network, where each node will keep a copy of the ledger, and then we need a consensus mechanism to make sure that the ledger is consistent throughout the network. We have also covered the topic of mining and how miners are rewarded for their work, as well as the extension to smart contracts. As we have seen, there are several potential applications. However, not all of them are good candidates for blockchain or distributed ledger technology. Unfortunately, there are several applications in the market that only make use of blockchain to justify the use of a cryptocurrency, whereas the application itself should not be distributed. In any case, the impact of this technology is at the moment unknown, and the reason is that we are not used to such systems. One example that you might be interested in looking at are the so-called decentralized autonomous organizations, or DAO for short. For those of you who want to start working with blockchain, we suggest the following reading material. First, the white paper from Bitcoin. Second, the yellow paper from Ethereum. Third, the white paper that describes the Ripple protocol consensus algorithm. And fourth, the white paper that describes Casper, which applies the proof-of-stake consensus mechanism on top of an existing proof-of-work-based blockchain. And finally, we highly recommend that you start working with Hyperledger. Hyperledger is an open-source blockchain technology hosted by the Linux Foundation, and you will certainly find many interesting projects there. Thanks for your attention.